let's start. I hope you can hear me. So this is week 8. This is the final week of this tissue engineering course. I'm Sonali. I'm a NPTEL-PMRF T-shape schemes PMM scholar for this course, and we have been doing these live sessions for the past 7 weeks, and this is our final week. We will be just quickly go through this week contents, and then we will be summarizing the whole week's courses content. Then we will see combined with whatever we have done. Let's take a summary. Let's go ahead. So this week we have learned about bone tissue engineering, vascular tissue engineering, and corneal tissue engineering, most of the application part. So bone tissue engineering, we have learned about the osteocytes and their cellular compartments like osteocytes, osteoblasts, osteoclasts, different generations of biomaterials, different types of biomaterials that are used for bone tissue engineering. Then we have studied about the vascular tissue engineering, what are the components there, process of designing the vascular tissue engineering implants, and as well as various bioreactor systems we have also learned. Then we have learned about the corneal tissue engineering, the detailed anatomy and physiology of cornea, and as well as the important properties that needs to be considered while designing a vascular tissue grafter, vascular tissue implant for tissue engineering applications. This we have learned. Okay. So let's start off with a question like you have a biocompatible material X which has very low elastic modulus, and you wish to use a particular material for bone tissue engineering. What are the material you will be using for compositing with material X for your application? So the question goes like that: if you have a biomaterial X which has low elastic modulus, then you wish to use the particular material for bone tissue engineering. Now, what other material you will composite with X for your application? The options are collagen, hydroxyapatite, both of the above can be used, and none of the above. What is the option? Try whatever the option. So it will be hydroxyapatite. Why I'm telling? So in the question we have mentioned that it has a very low elastic modulus. When we are saying, when in the question, it is like a revolved around question. So when the question is mentioning that some material has a very low elastic modulus, that means it is saying that we have a material that is elastic, that is more plastic in nature. It can be stretched, and that is not that much of a strong material that is needed for the bone tissue engineering. So what we need to do, we need to supplement with some other material like hydroxyapatite or some other. This hydroxyapatite, these are like strong materials that can be composited to increase the material strength. Right? So these questions, just think about what kind of material it is talking about. When it is mentioning a low elastic modulus, that means it can be stretched, and it is not that much of a strong material that is needed for the bone tissue engineering. Right? So whenever the question mentions the kind of material, it is low elastic modulus or high elastic modulus. It might be saying that very high elastic modulus, then what you can do? Very high elastic modulus, what it says, it is like a brittle material. So you can't use it as a bone graft. Right? So what we can do, we can composite with collagen, or we can mix it with something that will decrease its elastic modulus to the applicable things. Right? So that's how we can engineer this kind of bone grafts. This is just like a revolved around question. Okay. Alright. So the concepts of osteoinduction, osteoconduction, and osteointegration, these are clear, right? I think the discussion forum also have seen some osteoinduction and osteoconduction question. So it is clear, right? What is osteoinduction? What is osteoconduction and osteointegration? Osteointegration. Osteoinduction, osteoconduction, and osteointegration. These three things. It is clear, right? What is osteoinduction? Osteoinduction. Right. osteoconduction, osteoinduction, osteoconduction. Yeah, yeah. So osteoinduction means this is induced, just induction for the bone formation. Not like this is the implant is involved in there. It is like you are inducing the bone to form. If you have a fracture, you have a bone breaking, then you need the bone to form again. Right? This induction is osteoinduction. There is no material involved as such. Okay? You are hoping that immune cells and are brought up and they are made to stimulated to form osteoblast or pre-osteoblast or some cellular compartment. So this is the induction phase. And then osteoconduction comes, or osteoconduction means when you have an implant in there. So the bone cells, the bone forms upon the surface of the implant. Okay. So when we are talking about implants, then we are talking about osteoconduction. Okay. Then another fact is osseointegration. Osseointegration means when the implant is directly integrating with the bone. So whatever the, for example, if we have a bone breakage and we are implanting something, and the bone part where it is implanting or it is integrating with, that phenomena, this is called breaking. So here the implant will be coming. So this implant needs to be integrated with the bone. So this kind of phenomena is osseointegration. Okay. So osteoinduction, osteoconduction, and osseointegration. These three things needs to be clear. Okay. There might be some questions. Okay. Next, we have this TGF beta in the context of bone tissue engineering is the abbreviation of what? What is TGF beta? Migration growth factor, transformation growth factor, transforming growth factor, and transmigrating growth factor. What does TGF beta stand for? It's the kind of growth factor, very important growth factor for bone formation and bone tissue. No. It is transforming growth factor. Okay? It is not transformation, it is transforming growth factor. Okay? So that's why I put this options. So you know that yeah. So it is transforming growth factor. It sometimes might get confused regarding these names. So very attentively you have to read these names of the growth factors. Transforming growth factor. So move on to the next question. Osteomes, a cylindrical structure, are found in which part of the bone? Cortical bone, cancellous bone, and articular bone. Osteomes, where? Right, is the cortical. Okay. This question is the viscoelastic nature of bone is mainly due to the presence of what? Collagen, hydroxyapatite, trace minerals like magnesium, or osteoblast. What provides the viscoelasticity? Right. Anyone else? Viscoelasticity is given by collagen. Right? So remember the first question that we have talked about, some material that has a very high elastic modulus and what else needs to be considered. This is the straightforward version of the question. So if somebody wants that, he might want to, or she might want to revolve the question, she can revolve it like that also. So the options will remain the same. The questions will change in such a way that it might confuse. So don't get confused. Just think about what is the question you're asking. So here, viscoelasticity is provided by collagen. Then part of the bone which is relatively more porous is cancellous bone, cortical bone, both A and B, and articular bone. Which one? Part of the bone which is relatively more porous is which part? Go ahead. These are very different questions. These are like a scoring one. This directly it will ask and you will answer. It's cancellous bone, right? Another question is part of the bone wherein bone marrow is interspersed within. Which part? Cancellous, cortical, both A and B, and articular cartilage. Where we can find the bone marrow? is a porous in nature, where bone marrow cells can come in, there are various stem cells involved, that part of the lecture. So cancerous bone has this porous in nature. Right? Bone marrow is found in this cancerous bone nature. Right? Cortical bone is like that part where osteum is found. That osteon, the units, osteal units are found. So that part is osteons are related to its cortical bone. And when we are talking about bone marrow, where we can find the bone marrow dispersed, this kind of things we can find in the cancerous bone marrow. Then we have which of the following blood vessels experience higher pressure: elastic arteries, capillaries, aorta, and arterioles. Among these, which experiences highest blood pressure? The vascular tissue engineering lecture we have learned about. Why A? So I have got the option A also. Why A? Yeah, see, it is the aorta that experiences the most, when the heartbeat is there, this is the first thing that the blood pressure heartbeat. So that's the most pressurized region. The higher pressure is that by percent with the heart. Why using elastic arteries? Oh, okay, no, yeah, it is true. But when we're talking about arteries, directly elastic arteries, we are not talking about that elastic layer. Because when the question is asking like elastic arteries, it is not directly asking what it is just it is mentioning that the kind of arteries that is there. But when aorta, we might have that elastic region that is thicker. But yeah, elastic arteries doesn't mean that layer. It is meaning that when there is a direct option that is like the aorta, we will go with the aorta because this is direct option. In elastic arteries, there is a thicker layer of elastic material that is found in the real wall. That's why it's called elastic arteries. Yeah, it might be true, but we are not directly asking that. So when there is a direct option like this, we will go with aorta. Cells that are not found in healthy vasculature: smooth muscle cells, endothelial cells, fibroblastic cells, and adipocytes. Cells that are not found in healthy vasculature: smooth muscle cells, endothelial cells, fibroblastic cells, and adipocytes. What kind of cells we will not find in the vasculature? This is adipocytes, right? So what are the three layers in the vessel wall that we can find? Yeah. So what are the three layers? What are these layers called? These various layers. What are the name of those parts? Bones as well as arteries as well as cornea. These are very important parts in the anatomy of those three tissues that we were seeing. Even the skin in the previous lecture, in the previous week. So skin, and there are various tissue engineering applications. Yeah. Right. So these various layers, their names, particular names, try to remember them. So it will be important. This and the way they are layered. So there are various layers. One comes after another. What are the medial layers and what comes in between? This kind of layers. Layers names are very important. Okay. To be it before the final exam, it's very important to be these names also. Alright. So we have talked about stents briefly, and in the previous phase we have talked about making of stents. We have talked about. So what is stents? Stents are those kind of things that increases the diameter of the vessel. Right? But there are various stents, and those are called bioresorbable stents. So whatever the metallic stents we have, these stents are kind of permanent. So if there is no damage in the stains, then these stains will be there for almost like 25, 30 years or something like that. So their life is very long, this metal-based stains. But there are certain stains, polymer-based stains, that are bioresorbable stains. That means after a certain lifetime, that is tunable. After a certain lifetime, this polymer stains will be biodegraded and will be excreted or being used up in the human body. So there are various kinds of bioresorbable stains which are also called BRS that had come up in 2015 to 17 this time frame. There was a huge peak of research in the bioresorbable stains. Not only just those normal metal stains, and they in the metal stains and covered with polymeric with drugs. There are various anti-cholesterol drugs that incorporated with the stains wall. So this kind of drug-eluting stains came. And there is a nature of drug-eluting stain. That means there is a polymeric layer in the stains wall that will elute the various anti-cholesterol drug and various other kinds of drug for the treatment of this atherosclerosis or this thickening of the wall. Okay. So that is drug-eluting stain. And then they tried to enhance the material with the use of bioresorbable stain. So this stains after the particular application and after the thing, the cholesterol level and everything is balanced, then there might be a need to again retract the stain, take the stain out. But that will again need some another surgical intervention. Right? So bioresorbable stains came in where it will be implanted once, and then after the application period it will be taken out. It will be automatically degraded. Right? There are various materials like this styrofoam as well as PLNA, PLNA, PLGA, salicylate and other composite, magnesium, this kind of materials that are mentioned here. This kind of materials, and these are the examples of what kind of commercial stains that came up. This phantom, absorb, this kind of commercial material, and what are they composed of. So you can also study about. So this kind of polymeric material were used to fabricate this kind of bioresorbable stains. But problems arise when scientists saw the long-term effect of this. So basically in MIT in 2018, a human group made this paper where they mentioned like there are various problems, like pressing problems that need serious attention before use of this bioresorbable stains. There are two broad problems they have mentioned, that is the microstructural heterogeneity. So the outer surface of the stains that you can see here, the outer surface of the stains can be managed properly. This is manageable, but the inner core and the inner structure, there are various heterogeneity that was remained. And because of those heterogeneous structures that are present inside, these stains are getting brittle. So this stains needs to withstand a very high amount of pressure, right? So if there is a heterogeneity as a structural disability, so there it will be very much brittle in its nature. So there might be a problem of breaking of those stains, as well as there might be an issue of blockage of the particular vessel. Secondly, there is a non-uniform degradation rate. So because of this heterogeneity in their structure, the degradation rate also changes. Some part of the stain, maybe for example here, they start degrading faster, and ultimately there is a slower degradation. So because of that, this non-uniform degradation, the stains might break away and their application will be lost. So these kind of problems are also identified with the bioresorbable stains. So research is going on to find out what are the possible solutions that can be there. But the problem is whenever this kind of DRSs are coming out, so they are with a clinical application of only 6 months or 8 months. So very long study on the clinical application, clinical trials need to be done before they can be accepted in the market. So that is DRSs. Right. There is a matching match the following table. So it is about the corneal tissue integral, right? There are various layers, as you can remember. So first, we start with this. What is the corneal epithelium among the descriptions? What do you think would be the corneal epithelium? See this here is a protective layer. There are various layers of cells. There are black metallics based those structures that were found. Tier layer, that is everything is the epithelium part. Right? So corneal epithelium has a various cellular structure. This is also the acellular part. This is not acellular part. The epithelium is very much cellular. It has 4 or 5 layers of cells, and there is a various other structures that are very much important for their function. Right? So one B, that is 4 to 6 layer of stratified cells and protective layers. Next is Bowman's membrane. What will be there? Bowman's membrane. See, this D, Bowman membrane will be thinning out. With age, Bowman membrane will be thinning out, and decimal membrane will be thickened, right? Bowman membrane will thin out, and decimal membrane will thin up with age. Let's don't get confused. Bowman's membrane, this is also acellular layer. Decimal membrane is also acellular layer, but Bowman membrane will be thinning out as the age, as the percentages. Right? Thins with age. This with the whole thing, whole option. Okay? Here is the one that is thin. Thins with age. Right. Next is central stoma. Stoma will be this collagen fibers, regularly arranged collagen fiber that will be the transparency. Right? This is central stoma. Okay. Then we have the decimal membrane. What you talked about, that is thickens with age. Okay. It will thicken with age. Okay. Next is endothelium. Endothelium. All the options left, that is one layer of endothelial cells. Okay. Those will be solely transferred. So, what are the applications or what are the functions of those layers of cornea? And not only just the cornea, the tissue engineering approaches that has been taught in the series to study like name and their function. We can make a table of those, what are the structures and their anatomy and their function. You can make in a tabular form. You can study about it. Not get confused. And their layer by layer name. What is the name? What layer comes after what? Okay. So you can follow a particular layer, talk to what or something like that. It's a personal preference, but make a table and study about their name as well as the function. It's very important. This kind of the particular tissue engineering, like for the skin or cornea or vascular, as well as bone. Okay. This 4 kind of tissues we have talked about. So you study about their layers, okay? Layers and their functions. Okay. Right. Among which of the following in cornea these are not innervated: basement membrane, stoma, Bowman's membrane, and endothelium. Which of the following in cornea these are not innervated? It's directly mentioned in the slide. Not innervated means there is no nerves that is present. Okay. Not innervated, it is mentioned. Innervated, that is, there is no presence of nerves in there. So it is directly mentioned in the slide that is membrane as well as the endothelium, there is no presence of nerves in there. It is not innervated. Okay. So this is membrane and endothelium. Right? Okay. So this is the weak case, very weak case that we have learned about. So do study about those contents very attentively, as well as their particular cell type, their functions, and their layers. Okay. Alright. So previous weeks, whatever we have done, I just wanted to talk about very briefly, okay, and summarize the whole course. Okay. So, in the week 1, we have talked about what were the various kind of graft implants, the autograft, endograft, xenografts, right? Tissue engineering applications. We have also talked about what is tissue engineering, right? What kind of tissue engineering approach is there, methods of tissue engineering, and what kind of biomaterials that can be broadly used, what are the various cell sources. A brief overview of the whole tissue engineering thing we have learned, right? Various cell sources like autologous, allogeneic, we have talked about, right? Cell therapy, and various cell signaling molecules, how like what is signaling, what kind of signaling molecules that we use, how the growth factor works, what are the various kind of growth factors we are also talking about, right? Very briefly, for the treatment of articular cartilage, the cells of interest are harvested from a non-weight bearing area and cultured in vivo. The cells are then injected into a collagen membrane and finally membrane placed at the treatment site. What is the technique we are talking about? Very quickly. It is autologous chondrocyte implantation, right? Remember, we are taking the cells out, culturing it, and putting it with the placement or collagen membrane and placing it. It is a chondrocyte implantation. What was arthroscopic debridement? It is scooping of those areas so that the blood and certain cells come out and then collagen repair occurs. Then there was a mosaic plastic was also there. Remember, mosaic is small holes, takes and then takes of scaffolds that are the cartilage and bone takes are then inserted for the tissue there. That is mosaic plastic. Remember it this way. Mosaics we are getting. So we have mosaic floors, right? There are different colors of mosaics that are created. So here you remember like there are various holes that are created and plugs are inserted. So there are holes, you can remember it like these are mosaic of holes and you are plugging it with your bone and cartilage implants. Right? So this is mosaic plastic. Arthroscopic debridement. So you can remember it like scooping, if you can relate it with scooping of those areas so that blood comes out. Autologous chondrocyte implantation, that is the technique taking the cells out, culturing it and placing it with a collagen membrane. Then we have also got a microfracture surgery, that is small sharp peak to peak network of holes at the bone, right? And this kind of, so bloods and coming out, that is also microfracture surgery. Bloods and cells coming out, that is microfracture surgery. Oh, for arthroscopic debridement, this is scooping of the cartilage layer and then that is helping with the cartilage repair. So, yeah, arthroscopic debridement is just scooping, and microfracture is getting the fracture in the bone so that the blood and cells coming out and repair of the bone. So, microfracture, like, try to remember it, like microfracture, when we are talking about fracture, there bones and there are small peaks in the bone and cells and bloods are coming out. Okay, that is microfracture. And when we are talking about arthroscopic debridement, it is scooping of damaged cartilage. Right? Microfracture when talking about, then blood and cells are involved. Right? Arthroscopic debridement when talking about, it's just scooping of the thing. Okay? And mosaic plastic, like mosaic of holes, and you are implanting with the plates of collagen and bone. Right? That would relate to that way and remember. Alright. We have also talked about MASI, that is matrix induced autologous chondrocyte implantation. So same one surgery, cells are coming out, and then you are implanting with this with collagen matrix, so collagen 1 and 3. That is matrix induced. We are providing with the matrix, external matrix, right? Then there is also AMIC, that is autologous matrix induced. So you are taking the cells out. It is a single surgery technique. So you are taking the, you are just placing a matrix. It is cell-free technique. There is no cells are involved. Okay. So it is a cell-free technique, a single surgery technique. So here you are just incorporating the type 1, type 3 based collagen matrix. Okay. So that is autologous matrix induced chondrogenesis. And there is also chondrosphere. So there are chondrospheres are developed. There is a spherical chondrocyte bones, and they are implanted in the damaged cell. So that is it, right? Then there is bone grafts. So infused bone graft, used in anterior lumbar interval diffusion ALIF surgery using recombinant human bone morphogenic protein RHBMP2 using an absorbable sponge, collagen sponge. Once the bone graft is implanted, what are the various intermediate steps involved leading to the remodeling and ultimately resulting in normal bone? See, infused bone graft used in the ALIF surgery using recombinant human bone morphogenic protein RHBMP2 using an absorbable collagen sponge medium. What are the steps that are involved after the implant is there? Try to remember. It is implantation, chemotaxis, proliferation, differentiation, bone formation, angiogenesis, and removal. So you can remember it like ICP, DDR. ICP, DDR. When you are about infuse, you can think about the ICP, DDR. So implantation, chemotaxis, proliferation, differentiation, bone formation, and remodeling. Okay, so there are very much amount of steps that are involved in this. So you have to find out your way of remembering. So I remembered it like ICP, DDR. So implantation, chemotaxis, proliferation, differentiation, bone formation, and remodeling. These are the steps. Or you can remember the video that I have shown. From there you can also go. Okay. We have also talked about retinol, right? Shape memory effect. Retinol we have talked about. Retinol is an alloy of nickel and titanium. It is used in vascular stent because the alloy is super elastic. It can be deformed for easy implantation. Retinol can restore to its original shape inside the human body. Retinol does not have the property of shape memory. Straightforward question. Super elastic, can be deformed for easy implantation, and it has a shape memory. Okay. Shape memory effect, why it happens? I hope you remember. The slides are there, just go back to that. The two forms of material that is formed in the shape memory effect materials. Okay. Alright, then we came to the week 2. Week 2 we have talked about various scaffolds. What are the ECM-based scaffold, the decellularization process, what are the various natural polymers that are there, synthetic polymers, hydrogels, we have talked about various types of hydrogel across pigments, right? That is what we studied. So how the scaffolds are used, its tissue engineering application, desired properties, that is, it needs to be self-supporting, supporting promotes cell division, what are the various properties that are required for the scaffold formation? That we talked about various kinds of scaffold, the same components like what its function, and there is commercial ECM-based products we have also looked at. This kind of questions we have studied. Glucose responsive hydrogels, right? We have talked about, can act as an artificial pancreas to control blood glucose concentration. When the glucose concentration is high, the glucose diffuses into hydrogen and is converted to glucurononic acid. Gluconic acid, high glucose oxidation. What will happen to the pH after this conversion? That leads to hydrogen swelling and salinity. pH will increase, pH will decrease, pH remains constant. Why pH will decrease? Right. This is the mechanism how the pH will decrease and how the swelling occurs as the pH decreases. Remember, we have talked about week 5 also. This is the how the glucose is sensing hydrogen's bond, and what is the synthetic alternative, phenyl benzoic acid based groups that are used for formation of those synthetic materials. So while the commercial, that is a conventional one, the gluconic acid is formed, pH is reduced, and because of the osmotic pressure that is created, swelling of the hydrogen. Right? So this is one mechanism of conventional one. And using this kind of mechanism, the synthetic one was also there, that is phenyl boronic acid based, boronic acid PDA based smart chain system, that is glucosensing gel system was also used. Right? Then this question, which among the following statements are correct? Pore size can be controlled during salt leaching process. Gas pooling can be used to obtain interconnected pores, and while performing gas pooling, there is less control over the pore size and distribution of the salt leaching. Which among the following statements are correct? You remember the various kind of porous material forming strategies, gas forming, salt leaching, and other techniques, how regularized pore and interconnected pores, where you can find the regular pores. What is the technique you can find regularized pore? You can remember from that gas forming technique, salt leaching we have talked about. All are correct. Interconnected pores we can find with gas forming. For gas forming what we used ammonium bicarbonate. Carbon dioxide is generated when it's coming out. There is kind of pores we can find, right? But the pore size is different. It is not controlled in the gas forming. While controlled and regular pores we can find in salt leaching. Right? Remember that when we are using salt leaching, the pores may not be interconnected, but there is very much regularity. Interconnected pores we can find in the gas forming, but the pore regularization is not there. We cannot find the regular pore. Okay. So this is the difference we are talking about. Okay. Then we go to the week 3. What are the various stimuli responsive hydrogen that we have talked about? Bioceramics and their classification, scaffold fabrication strategies like leaching method, microsphere method, phase separation method, fiber sparing method, like electrosparing method, or decelerization 3D printing. Then self-assembly, 3D bioprinting, bio-wings, we have talked about, right? What is the self-assembly, how self-assembly works, we have talked about. So this kind of question, which of the following environmental stimuli can be used in stimuli responsive hydrogen? Select all the stimuli responsive hydrogen what we used. What kind of environmental stimuli? All of them. So stimuli responsive hydrogens can be articulated by using all of them. pH, electric field, glucose, light emission, light everything. Right? So stimuli responsive hydrogen, all pH, electric field, glucose, light. And another option would be stimuli responsive hydrogen. We talked about magnetic field, magnet responsive hydrogen. Right? With the help of external magnetic, the hydrogen's porosity changes, magnet responsive hydrogen. Okay. Then, which of the following methods following methods of bioceramic fabrication ensures high pore interconnectivity? H2O2 forming, sponge replica method, starch consolidation, salt leaching. Which of the following methods of bioceramic fabrication ensures high pore interconnectivity? Right? Why? Why do we get the high pore interconnectivity in sponge replica method? Because we already have a material upon which like a negative of the material that we have to fabricate. So we just pouring a certain mixture and heating it up. So the connectivity of the whole material is there. We cannot get much more interconnected porous structure than the sponge replica. Okay. Okay. That is the following options in the type order in relation to 3D printing. What are the steps? So there are steps are there. Steps needs to be remembered accordingly. Okay. In the correct order, we have to remember it. Options are buying, preparation, CT scan, cell culture and observation of tissue, CAD-based design, application, and droplet-based biology. All these options arrange it according to the order. Try to remember what were the steps that are needed for 3D printing. See, first we need to see. First, we for any bioprinting application, we need to first have a material, like have a structure that we need to bioprint. So we first need the like the G code, or like the material that we need to bioprint, like the material information. So for that, we need a CT scan that will give us a 3D information of the particular tissue. Then, from that 3D information, we will create a CAD-based model. Right? So we bring this scan data, put into my computer, and then using CAD-based system, like various softwares like AutoCAD or other SolidWorks, these kind of softwares are there. Using that, we will prepare a 3D CAD-based design. Then we'll go to the buying preparation. Right? Using some kind of material, we need to prepare a scaffold. Right? Then we will prepare the bio. Then we will bioprint that material using the whatever the design that we have made. Then we will whatever the cells we have encapsulated while preparing the bio, we will then culture it, cell culture and maturation. The cell will culture and mature the tissue of construct, and we will have the application. So think about it in a series of events you are performing for having a 3D tissue. Right? You will first have a design, then you will prepare the design in such a way that it can be printed. For example, if you need to print a page, letter through a printer. At first, you have to write it. Right? You will write it. For example, this is the example like we are preparing a CT scan and CAD-based design. Then we will be printing it. Right? Printing. Then we will be printing it. After that, we will be culturing it, and then our particular application will be made. Right? Like in a stepwise manner, stepwise event-based manner. Try to remember it. Okay. All right. Moving on to the week 4. Week 4, we talked about the characterization, surface characterization, mechanical characterization, biological characterization. Surface characterization, we have talked about contact angle measurement, volumeters, right? For example, what is the contact angle of a hydrophobic material? It would be greater than 90 or less than 90. Hydrophobic. Hydrophobic material will have a contact angle of greater than 90. Hydrophilic, less than 90. You are dropping a droplet of water. If the surface is hydrophobic, the contact angle will be more. That is, the water droplet will be much more round. It will not spread in the material. Right? Try to see it in that way. You are dropping a drop of water upon a material surface. It is hydrophobic. You are asking the question. It is hydrophobic material. When the droplet will touch the surface, it will not spread over the material. It will just try to gather in a particular round shape. So if we are finding a round shape, what will be there? The contact angle will be more, right? But when there will be a flat surface, like if it is a hydrophilic surface, the water touches, it will spray. If we draw the tangent, there angle will be less. So the contact angle will also be less. What is contact angle? It is from the contact to a tangent is drawn along the drop circumference. That is the contact angle. So if you are having a hydrophobic round object, its contact angle is more. If there is the water droplet is spreading, its contact angle will be less. That's why hydrophobic contact angle is more, greater than 90. Hydrophilic contact angle is less than 90. Whenever there is a contact angle question, right? What are the other surface characterization techniques? Efficient, we talked about AFM, XPS. So atomic level molecular information, which technique we can get from SEM or HTM or AFM. Precise atomic level information for conductive material. For conductive materials, precise atomic information we can get it from HTM also, right? HTM, it's scanning tunneling microscope. Tunneling current is created, right? There is a material, particular conductive material, and we use a particular type of conductive probe, so that the tunneling current is created between the material surface and the probe. And the probe, as it goes through the material, it depending upon the type of element that is present, and the topography of the material. This tunneling current changes, and depending upon which we get the atomic resolution of the current of material, we get the surface characterization. That is STM. But for non-conductive material, we cannot perform this. For that, we need the AFM. That's the modification of this STM. There is like tapping. There is three modes of AFM: contact, non-contact, tapping. Remember? So contact mode, we get for not all material we can get a contact mode. That is metallic material, we can go to contact mode AFM. For biological samples, we did the tapping mode of AFM. Okay. So this is a modification of the STM. So there is this AFM, atomic force microscopy, and same we get the surface image, which is it's not giving the atomic level data. Right. So these techniques we have talked about. Mechanical characterization. We used rheometer, universal tensile machine, UTM, right? How the data is generated, what is the various properties of the material, right? Elastic property, plasticity, plastic property, and how the metallic and polymers properties changes. Right? Biological characterization we have talked about, in vitro characterization, in vivo assays, hemocompatibility test, and like scratch assays, cell migration assays, this kind of assays we have talked about. Okay. Example of the question: which of the following is not a biological characterization method for a biomaterial? Protein absorption study, blood compatibility study, thermobarometric analysis, and bacterial addition study. Not a biological characterization. Right. TGA, what it gives? TGA gives the data of a material, the property of what are the various thermal property of the material. We get the thermobarometric material. Like if you raise a temperature and then you start raising the temperature, how its weight changes. That kind of data we can find with the TGA, thermobarometric analysis. Right? But protein absorption study, blood compatibility study, bacterial addition study, these studies give the biological characterization. Right? Then we have talked about where to measure the porosity of your sample, what techniques among the following you can follow for the purpose for porosity measurement. Bent, NMR, mercury porosity, same. Porosity measurement. All four, right? Why all four we have talked about? Bent method we have talked about gas, nitrogen gas, desorption, absorption property using the nitrogen gas absorption property. Bent method is there. NMR is sometimes used for the porosity measurement for particular kind of material. Mercury porosimetry is classically used. Same is also used. All four. Okay. Okay. This question is also come up in your quiz. Okay. You have been given a task of checking if the scaffold you have fabricated can help cellular migration. What test to be performed for this? Compatibility, mutagenicity, scratch assay, inactivity assay. Cellular migration, you need to study about what test to be performed. XTT assay is particularly used for measuring its viability, how the viability remains for the particular sample, not cellular migration studies. See, entity if we are using, entity and XTT we can do it. So entity if we are using the formation crystal that is created, we need to disrupt the cells to dissolve the formation crystal to check the cell's viability and cells how the cells are dividing, how are the cells check. Okay, it's metabolism. To check its metabolism, we can perform these two assays, like entity and XTT. Entity will form a formation crystal that only be dissolved by DNSO. And that's function. DNSO can dissolve that formation crystal. But XTT and this kind of material, XTT assay we can perform like it is not it is from the media only we can find the data. So we do not have to disrupt the cell. So we can check at a time point that how the cells are dividing and what kind of properties the cells showing using the XTTS. But these assays are not particularly directly used for the cell migration studies. But this scratch assay is one of the examples. Scratch assay is like you are growing a cell there, then you are creating a scratch using just like a pipette tip, or you can just creating a scratch, and after that you are seeing it, the cells migration, like cells are migrating through the scratch. So that you can do with the scratch assay for cellular migration. XTTS is not directly used. Okay. It's okay. Alright. Then in the week 5, we talked about cell sources, stem cells particularly. What are the various kind of stem cells, pluripotent, multipotent stem cell niches, how they are important, how various stem cell niches changes their differentiation pattern, right? Then cell isolation techniques, cell harvesting, cell retrieval methods, cell differentiation, cell identification techniques, right? Then density guidance, centrifugation, FACS, MAX, we talked about tissue dynamics and cell differentiation, hematopoiesis, factor regulation, the factor of regulating various differentiation pattern. Then various blood cell lineages, cell differentiation to the various blood cells and how they differentiating, these kind of things we are talking about, right? Especially stem cell differentiation, how the stem cell, what are the various kind of stem cells in the from embryonic to the particular tissue, differentiated tissue, how the stem cell behavior changes. These things we are talking about. Embryonic stem cell, what are the examples? What is embryonic stem cell? Pluripotent, multipotent, or unipotent? Embryonic stem cells. What kind of cells are those? Embryonic stem cells. Right. Pluripotent. See, remember from that chart, the embryonic stem cells, what are the embryonic stem cells? The plastocyst stage, after that, those interembryonic stem cells, like a layer of cells, and in the middle, there is a cluster of cells. Those are called the embryonic stem cells. They have the property of differentiation into any kind of cell. Any kind of cells, they cannot cell line. Any kind of cells, we can make. Like our body is constituted of from those cells only. So those are very high in their differentiation potential. So they are pluripotent. But as they keep on differentiating, like for example our muscle stem cells, they are unipotent. So from there we only get the muscles. Right? So their differentiation potential is very much less. They can divide into particular type of cells. Right? So like that. Try to remember, go through those things. Those are really important. Differentiation potentials, what kind of cells are what. Right? Okay. In asymmetric cell division, two daughter cells are identical, non-identical, differentiated. Asymmetric cell division, where we can find it? What kind of cells we can get the asymmetric cell division? Right. Right. What kind of cells? Stem cells. Stem cells also. Like one kind. Redifferentiation. Like stem cells are given the asymmetry. Like one kind produces a similar kind of cells that has a differentiation potential, and one lineage down of the differentiation. Right? Of stem cells. One keeps the reserve of the stem cell niche, and another is differentiated to the particular type of cell, like particular type of lineage it is specific to. So that is the asymmetric cell division, right? These options. Select that correctly. First. It's non-identical, right? Asymmetric cell division, we always get a non-identical cell. An example may be stem cells. One will keep its niche population, and another will be giving a particular lineage cell. That is one example. Right? Okay. Facts uses dash in order to assign specific cells. What is that? Surface marker, density, size, and morphology. Four options. Which option or which the facts uses for cell identification? surface markers, right? Yeah. Okay. Facts, max, how max or uses magnetic activities use or facts, process activities use on what are the principles, how it is used. Okay. Then week 6, cell adhesion, cell migration, signaling and biomolecular delivery, bioreactors, and challenges in tissue engineering. This is the broad topics we are talking about cell adhesion properties, how the cell adhesion, what are the key mediators of cell adhesions, integrate their various receptors, their receptor properties, what are the particular amino acid sequences, RGT sequences that we use, what are the AC property that is changed because of the use of those kind of particular sequences. So this things we have talked about in week 6, right? For example, in the cell surface adhesion, any negatively charged surface will induce what? Positively charged surface will induce what? It will attract. Negatively charged will attract or repulse. Positively charged will attract or repulse. Always remember cells are negatively charged. So when there is a negatively charged surface, so they will always get a repulsion, right? When there is a positively charged surface, it will get an attraction. Right? That's why your classical tissue culture plates are positively charged. Right? Polyl lysine protein, we perform lysine is positively charged amino acid. When there's this kind of positively charged surface, cells try to act. Right? Now, in order to study cell migration properties, which amount of following assays can be performed? We have just talked about scratch acid, Corneal chamber acid, micropattern based acid, fluorescent leveling, followed by nice cell measurement. In order to study cell migration properties. Right? What other options we have studied? Scratch acid is absolutely right. All of the options are right. Voiding chamber acid we have talked about, remember? This kind of voiding chambers. This is the micropattern acid. See, there are various kind of patterns that are created, and depending upon which we get the cell migration micropattern and microfluidic based acid. This is the kind of voiding chamber we have talked about, right? The particular cells are grown in the upper chamber, then the cells are migrating towards the bottom chamber of the cell tissue culture where from their property we can quantitatively detect the cellular migration, voiding chamber based acid, right? So all the options actually voiding chamber micropattern acid, fluorescent leveling, followed by live cell imaging. So this all four can be studied for cell migration. Okay, scratch acid, voiding chamber based acid, micropattern based acid, and fluorescent leveling and cell tracking. Right? Alright. Desmoso and hemodesmosomes are examples of what? Tight junction, NPTEL junction, and communication junction. We talk about various cell junctions, tight junction, anchoring junctions, and what are the properties of the proteins involved in the tight junction and anchoring junctions. Desmosomes and hemodesmosomes are example of anchoring junctions. Right? Get back to those slides. What are the examples? What kind of junctions are the anchoring junctions? Desmosomes and hemodesmosomes are classical examples of anchoring junctions. Right? Here, along trying to revise. There is sufficient time to revise. Do revise quickly. Try to revise at least 2-3 weeks on, and you will be completing it before the exam. Try to revise it as many times as you can. So these confusions will go away. Try to note it down. These points, this questions I am particularly taking because this is the confusing part where confusions may happen. Right? So this kind of parts you need to identify and note it down so that you don't get confused in the exam. Right? Alright. The term tax is associated with what? What kind of migration? Random migration, directed migration, both random and directed, and neither random directed. What kind of migration we are talking about when we are talking about term taxes? Right, directed migration. Okay, alright. Week 7 we have talked about host integration immune responses and bioethics, tissue engineering, like how the bioethics creates the various ethical dilemmas with tissue engineering, right? Various immune responses, very important. Adaptive immune responses, innate immune responses, what are the cells involved, how the cells properly changes, right? Multinucleated cells, how they are important. And skin tissue engineering we have also talked about, right? Skin tissue engineering, what are the various approaches for the skin tissue engineering, right? So we talked about this. Identify the option that describe the phases of normal wound healing process in correct order. See, the orders questions are very important. We had a detailed discussion last week. hemostasis or homeostasis, whatever is written. See, I was reading it as homeostasis previously. It was written hemostasis or homeostasis. Homeostasis event also occurs in the perspective of mechanobiology. Homeostasis will also occur. So that's why I was reading it in homeostasis. But whatever it is written, hemostasis or homeostasis, the correct order is hemostasis, or homeostasis, inflammatory, proliferative, and rheumatoid. Right. This is the correct order. Then various skin models, the in vitro skin models we have talked about. These are the examples of various kind of artificial 3D skin models. In the opinion of the ethical dilemmas that we have talked about, it is very much important that we devise a more realistic 3D in vitro model. So these are the dynamic fluid flow models, the dynamic shear forces of fluid flow can be incorporated in our 3D models. So these kind of models we have talked about. These are the examples for your reference that this kind of work is going on. Right. This is also a cellular like electrospinning. So electrospinning solution as well as cells are directly electrospun for tissue engineering. These kind of handheld devices. So we are trying to get to the position where it will be portable enough so that anywhere application is possible. Right? From remote to remote location, we can apply on devices. So that's the purpose of this kind of devices of tissue engineering approaches. Right? So this is from my side. We wanted to talk about the whole courses contents as well as this will complete. If you have any questions, please do ask in the discussion forum. Even after these sessions will not be there for the next week, but the discussion forum is open. You can ask as many questions, we will be there to answer those questions and any kind of doubts or. So do interact with the TAs and write as many questions as you wish. Any questions you have now? So I hope you have got the overview of the whole course and you have got to the point where you can identify what are those areas that you need to gain more. Okay? So thank you everyone. I should be thanking you guys for joining in, and we have had a very informative couple of months here. And I hope you get to all the success that you want. Okay. Right. Thank you for joining all this once again. So, you write in the discussion forum and study hard for the examinations.